Okay, let's briefly talk about Ethernet. Ethernet is really the dominant link layer protocol in practice. Um, let's think about why that is, and maybe talk a little bit about some of its history and some of its design. Okay, you see those four words there. Those four all describe Ethernet, and if you see that, it should make sense why Ethernet is so popular. It was designed to be very simple, right? And when you make something simple, it has other benefits, like it's probably fast, and it probably ends up being cheaper if it's simple to implement. It also helps that it was really first, so it became very widely used. It was always cheap, and even when other perhaps more elegant, more complex link layer protocols came out, Ethernet was always able to kind of step up its game, increase from one speed to the next speed, and be fast enough and still be cheap. And so that's why it's still a winner. The picture here is actually one of the original drawing designs from the guy who created it, a guy named Metcalf is his last name. Um, and it shows you the original idea is in yellow, there's this shared wire that's terminated on both ends. And to connect to the wire, you would actually have to tap, like cut into the wire and be physically, kind of tapped into it. And you can see this is the computer here. This is how it would interface to the wire, which he called the ether, right? So the ether is like the shared medium that everybody's communicating over. We've come a long way since then, but it's still really the theoretical basis for where we are today. So originally, this was a very bus-centered topology. And by bus, I mean there was one wire, which was the one medium through which all computers communicated, which means if two people are talking on the bus, on the wire at the same time, what happens?
Collision.
Right, that's collision. That's noise, and you can't hear it. So they say that they're on the same collision domain, so that's one domain, and if multiple people are talking at the same time, that's garbage. We're going to be using the CSMA CD. Remember, carrier sense, that means listen first, and CD means collision detection. When you hear the collision, you stop, and then you try again later, according to some algorithm. Today, the networks really look like this star topology. They use a switch instead of a hub. The switch in the center is, you can imagine there are spokes coming off of it. What happens inside the switch may actually be a hub, may actually be a bus. That is, that there is this shared wire over which everyone's communicating. That's called a hub. Generally, a switch, which we'll talk about later, actually separates each of these into its own collision domain. So the switch will prevent multiple people from talking at the same time, basically, and not send one message to everybody. Let's look at the structure for Ethernet. This kind of gives us a feel for how the packet design is and so what features it supports. The first 7 bytes is called the preamble, and the preamble is a way of synchronizing the nodes. So it's a way so that the nodes know, they can kind of hear the beat. The preamble is just this pattern. It's 6 of these bytes, 10, 10, 10, 10, 10, and then the 7th one looks like this. So if you were to arrange 6 of these with one of these on the end, that's the preamble of every packet. So that sequence, that pattern, is a way of telling everybody, hey, we're about to start a frame. Okay? So everybody knows to listen for that, and it helps the clock stay in sync. You see, next we have the 48-bit destination address. the 48-bit source address, 48 bits, that's going to be 6 bytes, yeah? So 6 and 6. There is, well, let's go ahead. Right, we've got 2 addresses, 6 bytes each. The type is a code that represents what higher layer protocol, what network protocol is encapsulated in this frame. So there's a special code that means IP, and you know that's mostly IP these days, but there used to be a lot more of a kind of a battle for the network layer. Not many network protocols really around as much now. This type field reminds us of something we've seen before. You remember this? We've seen it multiple times, right? This is the glue that binds together the link layer and the network layer. We had another one of these in the IP datagrams that said this is the type of segment that I'm holding, right? There's a code for UDP, a code for TCP. We saw this again between TCP and the application layer, and then we had a special word for that. What was that? It's a code that kind of lets the higher level demultiplex. Right? What is it that number that says this is the application layer that you want this segment to go to? Like if there's an 80 in this, it means this is a web packet, a web segment. Right. Remember port numbers? All those 3 things are really accomplishing the same goal. It's a code that says this is the kind of packet that I'm carrying. The last part is the CRC bits. You remember that cyclic redundancy check? We talked about all that modulo 2 arithmetic and dividing those really long numbers. Remember the data bits and the generator and all that, and the R. All right, so running that algorithm is what this what goes in that CRC. If an error is detected, the frame is dropped. So it would be up to a higher level protocol to recover from those drop packets. This is another way of looking at the link layer. We've got the, you see in this diagram, they didn't include the preamble. They didn't really even consider that part of the frame. I could see that either way. But we've got 2 12-byte MAC addresses, a type, and a payload. The payload, you can see, can be between 46 and 1,500 bytes. Well, that 1,500 bytes is the maximum size of a frame. This is why in the last chapter we talked about breaking IP datagrams into 1,500 byte fragments. Remember that? And that's just because commonly IP is going to be held within, an IP datagram is going to be held within an Ethernet frame. That's where that number comes from. And the CRC is 4 bytes. Okay, let's talk about some properties of how the Ethernet protocol works. It is an unreliable and connectionless service, so there's no handshaking, no setup ahead of time, and it's unreliable. There aren't acknowledgments or negative acknowledgments. If the receiving NIC doesn't send anything else back, the stream of datagrams passed to the network layer, or passed to IP, it could be incomplete. It could have gaps, missing datagrams. But if TCP is running on top of that, then the gaps will be filled in. Ethernet uses unslotted CSMA CD. Okay, let's think about what that means. It's unslotted. That means you can send anytime you want to. It's CSMA, that's carrier sense multiple access. That means you listen first before you start transmitting. And CD means collisions are detected and you stop if you detect a collision. Here is sort of the algorithm, you might say, sort of written in pseudocode for CSMA CD for Ethernet. We're going to receive a datagram and create a frame, right? We're receiving it from the higher level. We'll listen to the channel, and if the channel is idle, we'll start transmitting the frame. Otherwise, we're going to wait until the channel is idle and then transmit. And if somebody else is talking, we'll wait for them to finish. Okay. What if a collision is detected? If there's somebody else transmitting while we're transmitting, we will abort the transmission, but we will send a jam signal. The jam signal is a way of sending out a message to give the other guy time to hear you so that he'll know to stop as well. Okay? The last part here is kind of the most elegant part of it. And it explains the algorithm for determining how long you wait to resend. In the past, we talked about having some probability P. Remember flipping the coin, right? That would be like a 50% probability to retransmit. Ethernet is smarter than that. What Ethernet does is it remembers how many times a collision has happened for this frame. And it's going to choose a random number between 0 and 2 to the m minus 1. And it's going to wait a time that's proportional to that number. All right, and this is, it's going to wait that number times 512 bit times, where a bit time is the time that it takes to send one bit. So it's going to wait that much time and then resend. Let's talk about what this exponential backoff, what this means. The first time that a collision happens, m is going to be equal to what?
0. 1.
1. So if m equals 1, then we're going to choose a number between 0 and 2 to the m minus 1. We're just saying that's a number between 0 and
0.
right. Okay. If m equals 2, where does that put us at?
0 and 3.
0 and 2 to the 2 minus 1. Right? That's 3. Okay. And if m equals 3, what's that do for us?
8. Oh, yeah, that's 2.
So, you see what's happening here. Every time there's a collision, the range of possible wait times doubles. That's why it's exponential. The first time everybody who collides is going to flip a coin and get a number between 0 or 1, right? 50% chance of resending. The next time that window there's more possible chances. The next time it gets larger. All right, what's the point of that? What is it that this exponential backoff does? Why does it do that? Why not just stick between 0 and 1 every time? What you got?
Say it again.
So the question is, why go through this complexity of basically changing the probability of retransmitting the packet? Right? The first time you have a collision, this is for one packet. You're trying to send one frame. And if you collide, then you're going to choose a number between 0 and 1 and wait that long to retransmit. Now, you can imagine you're going to wait 0 seconds, retransmit immediately, or wait 1 second to retransmit. The next, if you choose one and you collide again, then you choose a number between 0 and 3, and you wait that many seconds, imagine, to retransmit. If you collide again on your second try, you choose a number between 0 and 7, and you wait that many seconds before you retransmit.
The chances of colliding get smaller and smaller.
Right, and why do we want to do that?
Make sure it goes through without wasting time.
Okay, so what's possibly happening? Why, if you can't get through the first time,
It's like
what might be the case? Why can't you get through?
There's a packet going through.
There's definitely another packet going through. Were you going to say something else?
Too many things are trying to broadcast at the same time.
All right, that's kind of what I was wanting you to get to. There might be 4 people trying to talk at the same time, but they don't know that. They just know that there's a collision happening. So by expanding this range, we're adapting the retransmission wait time to the number of senders. And we're doing it in a distributed way. Okay. The jam signal is 48 bits, and the purpose of that is to make sure that all other transmitters are aware of the collision. And as I said before, a bit time is the time it takes to send 1 bit. So if it's a 10 megabit per second Ethernet, it's 0.1 microsecond. If it were 100 megabit Ethernet, then it would be 0.01 microseconds. So that's just the way the time works out. This is what I was working through before. What is the goal of this exponential backoff? It's to adapt the retransmission attempts to the current load. So if you have a very heavy load, then we want to give a lot more possibilities for when you could retransmit between different times. And there's sort of what we wrote on the board about the number of the values of k that you would randomly choose one of, and for the number of collisions m. Okay. The CSMA CD, we might ask the question, how efficient is it? Remember we did this before for Aloha, slotted Aloha, and we showed them to be very inefficient, right? We're going to waste a lot of slots, a lot of bandwidth on empty or collisions. The book does this analysis. It's sort of quite a bit more complex. And this is how it turns out. The efficiency of Ethernet, CSMA CD, is 1 over 1 plus 5 times the maximum propagation delay divided by the time that it takes to transmit the maximum size frame. Okay? So notice the relationships, the kind of the dynamics of this. We would like efficiency to be 1, right? 100%. And how can we get that to happen? Well, if the propagation delay, as the propagation delay gets smaller, then it'll be 1 over 1 plus some small number. As the time to transmit the maximum size frame gets large, right? If that goes to infinity, this whole thing goes to 0, and it becomes close to 1 also. So that's kind of looking at it on the boundaries. Does that make sense? Why these properties would exist? Imagine if we're sending packets that are infinitely long, right? Once you have the medium and can start sending, nobody can interrupt you. So that would be highly efficient. It would be unfair, but it would be efficient. If you have very small propagation delays, right, that means you can very quickly send the packet. That means it's very unlikely that somebody can interrupt you and create a collision, right? So that's kind of what's going on there intuitively. There are several Ethernet standards defined in this 802.3 standard. It actually defines, the 802.3 standard defines link and physical layers. They have a common MAC protocol, which we have already seen, and common frame format that we've seen, but some differences at the physical layer in that the Ethernet standard can work over fiber or over copper. There's lots of different speeds of Ethernet as well that have developed over the years. You can see that those are almost see that they're the ones that have T in them are copper, twisted pair is what the T was for, and the ones that have the F, S, and B are for fiber. The last thing I wanted to mention here, and this is sort of about the closest that we're going to get to the physical layer in this class, is this thing called Manchester encoding, and it's the encoding scheme for Ethernet, or at least in 10 base T. Okay, let's imagine we want to send this stream of bits. 1, 0, 0, 0, 1, 0, 0. Okay? If we were to encode that in binary, that's going to be high, low, 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 high, low, 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 high, 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 high. Yeah? So that would be the naive way of encoding that digital information on a signal. All right, does that first step make sense? Okay, the problem with that is, if somebody's receiving that, how do they know if this is a 1 followed by 3 zeros or by 2 zeros? How can they distinguish between these subsequent values? All they see is high, low, high, low, high. Do you see that problem? What does it require? How could, if we're sending this stream right here, and the receiver is then receiving a stream that looks almost exactly like this, how can it decode the information? What does it have to know? It has to know exactly how wide each of one of these is, which means it has to be exactly synchronized to know this is the timing that was used to transmit this. Does that make sense? If it can't distinguish exactly how wide in time each of these is, then it can't know if this is 3 zeros or 2 zeros or 1 zeros, because it just looks like a 1 and then a 0. Does that make sense? All right. Synchronization is hard, and we would like to try to avoid that. And you've got to solve the problem somehow. Manchester encoding has an elegant solution to this. What it does is, instead of encoding a 1 as just a high signal value, it encodes 1s and 0s using transitions. So a 1 is a transition from high to low. A 0 is a transition from low to high. Low to high, low to high, high to low, low to high, low to high. You see what happened there? So the cool thing is, right, the other side, even though it doesn't know the exact timing, it can detect those transitions and see, okay, I see that it changed from low to high. That means 0. And then I can see, even without knowing the timing, it changed from high to low, that's a 1. So without having a global centralized clock, we can still keep everybody in sync, and we can distinguish the bits. So this is really physical layer stuff. This is the kind of things that electrical engineers are concerned about when they're designing mechanisms for encoding digital information onto signals. So if this is interesting to you, then you should be an electrical engineer, perhaps. And if this is not interesting to you, then you should not be an electrical engineer. All right. Questions on this? Very good. All right.